Hi, I'm
zoomed
Scott.
in.
I work with Justin and Derek for the Buck Boost Converter Design Lab. Specifications for our Buck Boost Converter would have a 12 volt input and have a 5 to 20 volt output. This is some of the design equipment that we used for our circuit, which included the MOSFET and a 555 timer. This is a circuit for our A-stable mode 555 timer. The 555 timer was going to be used to drive the MOSFET by changing the duty cycle. In order to change the duty cycle, we were going to have one adjustable resistor, which would have changed the duty cycle for us, which would have changed the on and off frequency of the MOSFET. The issues we had with this is by changing the duty cycle, we also changed the frequency, and that would not allow our circuit to work.
In order to find out which parameters we needed to design for and find out the capacitance and inductance values we would need in this circuit, we created this little MATLAB code. And what it does for you is it takes the 12 volt supply voltage that we're going to have, and then it takes your high voltage target of 20 volts, the low voltage target of 5 volts, and your specified switching frequency, which our initial design required 250 kilohertz. After it has those values, it'll calculate the duty cycle, the minimum inductance, and the minimum capacitance needed. So for our circuit, we determined that in order to get a 5 volt output, we would need a 29.4% duty cycle. And then to get the 20 volt output that we wanted, we would also need 62.5% duty cycle. And this is a fairly wide range. So then, off of our calculated inductance, we calculated that we would need a 2.8 microhenry inductor. And so we chose a 68 microhenry inductor to ensure that we would be in a continuous mode of operation. Our minimum capacitance for a 2.5% ripple was calculated to be 10 microhenry, microfarad, sorry. And so we chose an 18 microfarad capacitor to ensure that we were well below our ripple percentage. So then, after we calculated those values, we can now implement the circuit. So what we did first was we put it into PSpice, and we used the exact same model that we used in Lab 2 of this course. However, we were not able to get that to work. There were many issues with it, and our largest issue was that it was cutting off at 14 volts output, and it would never be able to reach the 20 volts. The speculation for this is that between the switch that we were using and some of the non-ideal parameters of the components, we were not able to get a clear simulation. After that, I tried implementing a simulation in Simulink, which is a MATLAB program as well. So here we have the circuit that I used. It's a 12 volt input, the 68 microhenry inductor with a very small resistance attached to it, and the 18 microfarad capacitor with a very small resistance as well. There's a pulse generator that would allow us to vary the duty cycle of the circuit, a transistor block that we used as our switch, our diode, and then we measured the output voltage and current through voltmeters and ammeters. So here's the simulation results for this circuit, and what we have is we have our 5 volt output on the top here, and as you can see, MATLAB does this in discrete time because with the pulse generator that they have for continuous time, you can't vary the duty cycle for a frequency. You can only create a square wave based on a frequency. So we had to implement this in discrete time, but as you can see, there is a 5 volt output on the top, and then there's a 1/2 amp load current, which is exactly what we would expect from this configuration. On this lower graph, we have our 20 volt output. As you can see here again, we have a nice 20 volt after the transient state, and we have a 2 amp output current. So that is exactly what we would expect.
Hi, my name is Derek. So this is the actual circuit that we ended up building. And we will get to that later in the actual simulation. Not the simulation. The implementation, sorry. We had lots of issues with actually building the circuit and getting it to work. Most of the issues were that our driver chips and MOSFETs would simply just burn up. We're not totally sure why this keeps happening, especially because when our simulation gives us all the correct outputs, we should be getting the correct outputs. But we're fairly sure it's because the MOSFET in the buck boost converter is not on ground. It is on the high side, so the source voltage will vary. So in order to keep using this MOSFET, we decided to use what's called a bootstrap circuit. And the bootstrap circuit is basically a capacitor and a diode, which is going to keep the gate voltage high enough when the MOSFET wants to turn on. We did use ICs that were specifically made for this purpose, and they still did not fulfill our goal. We had a lot of problems with that. So now we will go on to the actual circuit. Okay, so here's our actual circuit. We are running our MOSFET from a function generator, and here's our 2 volt input. Right now it is running at a 50% duty cycle, and we are getting a 1.3 volt output, which is to be expected because of the 0.7 volt diode drop. So if we go to a lower duty cycle, you can see the voltage decrease. Ideally, we would be having a 1 volt output, but because of the 0.7 diode drop, that we only get 0.3. Now if we go high, to the high duty cycle, we get a 2.5 volt output.